Okay, then I'm going to start with this boat model. And this is it's just a generic geometry I took from internet. That's a surface model, but the idea is to model this zone name called transom. Is where the motor and all the power of the motor is transmitted to the whole structure. And for the composite industry, it's important to have an structural analysis of this zone of the boat. Obviously, we are not going to simulate all the entire boat. We are going to work only with a portion of it. I've made a cut, an arbitrary cut of the geometry in some place. It's just a code, and we've made some simplifications. When we are going to work in ACP to model composite materials, it's important to planify in advance where are we going to apply the reinforcement. We can do it either in the space claim or discovery in the geometry in the geometry stage, or we can do it in ACP. But if we already know that we are going to apply our reinforcement, is more useful, is easier to do it in the geometry step. For example, I've made here, we know that this vertical surface is going to be connected to this other one. That's why I divided my geometry into surfaces in order to apply a future reinforcement here. But maybe we are not sure all the zones we need to apply a reinforcement, but we can do it later in the other interface. And that's easy. That's all. We have some different zones here. All are surface bodies. I've created these circles here to apply the motor load, and here these rectangles in order to apply the motor thrust. Okay, from the geometry side, I guess that's it's a simply an easy thing to do. And at the end, I applied some shared topology to connect the different body surfaces. Okay, then we are going to pass to the ACP. That's where the magic occurs. We are going to define all the composite structure. Here we are going to follow the tree in the same way we do it in any other Ansys interface. We're starting from the top and going to the end, defining everything we need. First, we have from the engineering data, we have the material. For example, here we have a unidirectional ply with these properties. Okay, and we are going to create a fabric with it. That means that here at this level, we have only the material definition. Then we can create one or more fabrics to be used in our model. For example, here I created one, but in this case, I assign a thickness of 1. That means 1 millimeter in this model. For the fabric, I could say that's all. Then we can create not only fabrics, but also stack-ups. For example, if we buy from the oops, I forgot the word, from the supplier, we buy our already prepared stack-up. For example, one layer of fabric 1 with an orientation of 0 degrees, a second one with 30, 45, 0, and so on. I've created a 7 layers stack up to define my composite structure. I could do by this way, or I can create all the levels by each fabric. but it will not be so efficient way to do it. But it's the same at the end. It's the same thing, because when we're creating our model, we are assigning a layer element. At the end, we are going to assign each layer for each layer of the element. At the end, it's the same thing at the end, but defining in this way is easier to configure the model. Then the important thing creating this kind of models, we have to create a lot of element sets that are the same that the name selection, because we have to create everything based in the name selection definitions. For example, we have here an element set named all elements, but we have a lot of them in order to define, for example, here a reinforcement. We have here exterior and the other and something like that. We have several element sets. And then we have, for example, here several rosets that that they are only coordinate systems. It's the same thing, but we use to define every layer of our composite structure. Then the most important thing are the oriented selection sets. That's the real surface we are going to apply each layer of the composite material. That means, for example, here I've created one to model the transom part. We can see we have one layer, one superior layer here, and a bottom layer here, and some lateral one, like this one vertical that envelops our transom. But here we can see there are some yellow vectors. These vectors show us the reference direction of this oriented selection set. That means that is the 0-degree angle for this part. We can have another direction different to this one to define the other parts of the same model. For example, here in some lateral, let me see, bottom, for example, it's the same. For example, here in this part, in this yellow zone, the 0-degree direction is vertical, following the geometry of our mold of our boat at the end. That's the idea to work in ACP. We need to define all these reference direction in order to define the angle where we are going to orient our fibers then. But this kind of vector of the direction is defined in order to see how we are going to construct this structure. For example, we must define also the direction of the ply. That means in which direction are we going to stack every layer we add in the model. For example, we can add the layers to the outside or in the inside of the boat. In this case, I define it in that way in order to add all the plies to the exterior. We do the same thing for each zone. For example, here we can see our reference vector is not horizontal, is defined following the edge of the blue geometry. We can see that here. And that's that's the way we really construct this kind of parts. Okay, after that, the thing to do is to really define the layers, the stack-ups. How are we going to do that? We are going to do it using the modeling groups. These modeling groups are where we really apply the layers. For example, here in the transom, we defined a modeling ply for all this zone, for all this geometry, for all these surfaces. But at the end, we are applying just one time the modeling ply using the fabric I define, the stack up I define, this one. For example, here, if I see the properties here, I can see that I am using the stack up one, and I used one number of layers. I can use, for example, 3 times, 4 times, any times the 7 layers of the stack up one, or I can add, for example, one time the stack up one, and then one time or 2 times the individual fabric. I can define it as I wish. Cancel. Then we can see here we are defined that, and for example, in the body we have two layers. That means I apply 14 layers in these zones. That's why I construct my composite in that way. We can see we have any of these here. Once the composite layup is constructed, we can see, for example, I am going to hide that, and I am going to show. Let me orient the view like that. Okay. For example, here we can see the green vectors, who are the vectors indicating the orientation of this layer. But if I pick the second one, I can see the yellow vector are oriented. The green vector is turned in reference to the yellow one. That means that it has, I guess, 30 degrees. The third layer, 40, 45, 0 degrees, minus 45, minus 30, and again 0. That's why we define our place. And in this way, we can work with this structure. In that way, we can do that. And we continue with every zone we want. We can define more layers, less layers in each zone, and we construct our structure in a way we want. Here, for example, I applied some reinforcement. We can see them here. For example, in this zone, I applied this one in the taking the red and the yellow areas we see here. For example, here we have 2 times 7 layers. We are using the fabric, the stack up 2 times, and we have this kind of direction. This one, for example, is the main orientation. If we see here, we have an angle of 30 degrees. This is the angle between the stack up we created, measured with the oriented selection set defined. For example, here, this zone is geometrical. We have only here. This is 0 degrees, but my reinforcement, my fabric, are oriented and 30 degrees with that. Okay. And for example, once we have created all of our structure, we can visualize, is very important. For example, we can see a section cut. We can see this kind of visualization where we can see the layers we created. We can see where are the main layer, and then where the reinforcements are placed, which one is over which one is very important. We can see that in order to really define our composite structure. Here we have, for example, we have a base layer here. We have a reinforcement. We can see it in the middle. Then we applied another layer over all that. That is a common way to construct the composite materials. And this final layer has been applied only in this green zone. We can see here the colors are corresponding to the thickness of the total structure. That means that in the green zone we have 21, and in the blue we have maybe 12. Then how I define this? If you return to the geometry, we can see that there are no divisions in this surface. In that way, we apply it in ACP. We define it in ACP using one tool named, for example, selection rules, like that, where, for example, using two parallel planes, we can limit our zone where we are applying the layer of the stack up of material. And that's simply like a filter where we can define our composite structure. At the end, this is the way we use it. We define every layer, every orientation, every thickness, and that's all. In each section we want to model. Then we are going to move to the structural simulation. That means that if we see that in Workbench, we have a model, an ACP model, where we define our material, our geometry, then a shell mesh with no material, with no thickness. It's only a shell to construct our ACP model. Then we connect this model to an static or another structural model. It may be a modal, a harmonic, and so on, and any kind of analysis. Then we are going to define the rest of our simulation. It's exactly the same thing from this point. The task we developed in ACP is to define the layers and the orientation and the materials. But here in mechanical, we are going to define the rest of the simulation. For example, here we can see we have our mesh. We see a superimposed mesh. That's why we can see that because I am importing another solid mesh in order to model the interior body who is in the transom zone. That means a balsa body who is to stiff all this structure. But if I hide it, hide body, I have really my ACP mesh. We can see here all the imported plies in the same way we already defined it, with the same thing exactly. And all the name selection also that we define, it's recommended to define it in the geometry definitions, maybe in Discovery or in Space Claim, to have more control of them. And here we define all the rest, the simulation. Here, for the demo, I just applied a fixed support. And for the weight, using some remote loads in that way, according to the center of mass of the motor, and the thrust in the position of the impeller. Okay, then it's the same thing like any another analysis. We define our simulation, our I don't know, our time steps and so on. Then we can see the classical results. In this case, the total deformation is for all the structure. That means that all the layers are moving together. We are not separating them. Here is obvious we have no reinforcement here. That's why we have our maximum here. But the most important thing is the composite special results. For example, we can define a composite failure tool where we are going to choose some criteria for the composite industry that are going to evaluate every layer for every ply, for every part in our model. That is the interesting part, because we need to evaluate. We don't know which layer is going to fail. We need to know that. And maybe we are adding a lot of layers in some zones. We need to optimize our structure, retiring some layers, doing searching for fabrication, for a cheaper fabrication. Then we are going to choose some criteria. There are a lot of them. For example, I activated here this one, whoops, this one, pack, and so on. For each criteria, we have to define its parameters. That means we have to know which value we are going to use here. For the demo, I use the same for by default, but as always, if you have some better information, you can use it. Then we have our response. I defined some inverse reverse factor. That means if we have a value greater than 1, that means that at least one ply has failed. Any value under 1 is a safe place. Then we can see here, for example, by element, we can see the evaluation of all the criteria we defined. Here, for example, I found that some kind of weird, but the labels are floating, are displaced. This is some difficult to see sometimes. Here, for example, we can identify some elements who have any possibility to be failed. For example, here, and so on. For each element, we have just one color because over all the element, we have the same value of the inverse reserve factor. For example, here we have this one. We are going to suppose this one is an interesting zone. We are going to interpret this with this label we have here. For example, it says E2T22. That means that the critical criteria for this element is an strain failure criteria because it's E. 2 because it's the second direction. T, I don't remember the T, but the 22nd, that means it's the 22nd layer of all my composite in this element. We have seen that here. We can see, for example, if I return here, I can see there are a lot of layers in this zone. That means that is the 22nd who has failed, or has the biggest value. We can perform a detailed zoom in this element. For example, using this tool, we can create sampling point where I can here I select really an element, and we have like a sensor in this point. We can see this kind of information. For example, this zone, the first zone, we see the real stack all the plies. We have 4 times. That means 28 layers at this point. All of them are created from the same material in the same thickness, but that's because is the way I created my structure. But we can evaluate, for example, here the strain. This is the first principle, but we can evaluate any other. Okay, then the principle like that. Okay, then we can evaluate the failure modes in this zone. For example, we have seen the E2T was the criteria, the greatest criteria at this layer. But for example, for this other layer, we have a different one. This is a POC for matrix. I don't know what the A means, but it's another criteria who is the biggest at this layer. But here is the E2T, and its value is around 0.852, I don't know. But in that way, we can see the evaluation of each layer. And that's the interesting. For example, this layer is, we can see is not apporting to the structural in this point. Maybe we can we can retire from the structure. Maybe there is not any utility of this layer here. At the end, we have the polar properties of all the composite layer. We have a resultant like that. This is the angle where we have the E1, the E2, and the G model, the shear model in at this point. That is mainly our results that we can see here. Is the as you can see, is the same workflow. The only additional step is to create our ACP model, but at the end we are performing another structural analysis as any other. Okay, I guess that's all for my side. I would like to know if there are some questions.